Hi everyone, let me introduce myself. My name is Wang Ki, and this is my group member Matt, Uki, Raman, and Suferi. Ourselves group going to present design of Chebyshev low pass filter, and this is our objective is to study and understand the basic operation of Chebyshev filter and to design a low pass Chebyshev filter to simulate Chebyshev filter using P-Spy. Okay, let's explain what is a low-pass Chebyshev filter. This filter is a device or process that remove unwanted component or features from a signal. Every system is a filter. The system has a frequency response that attenuates some frequency more than others. And the Chebyshev filter are used to separate one band of frequency from another, and is the best approximation to the ideal response of any filter of a specific order and ripple. To put in other words, Chebyshev filter can minimize the error between the idealized and the actual filter characteristic over the range of the filter, but with ripple is in the passband. And Chebyshev filter achieve a stepper roll-off than the Butterworth filter. Thus, it has more passband filter, which is type 1, and stopband ripple, which is type 2. Over here, we can see the different type 1 and type 2 of the filter. Type 1 filter of Chebyshev polynomial has an all-pole transfer function, and the filters allows only ripple in the passband. And the type 2 of Chebyshev filter has both pole and zeros and allows only ripple in the stopband. However, type 2 filter are seldom to use. And here, you can see the type 1 Chebyshev low pass filter has an equilibrium passband and a monotonically decreasing stopband. And this here is the formula of the magnitude response. And so where is the N is a filter order, is a user supplies parameter that control the amount of the passband ripple. And the omega p here is the upper passband edge. Now we're going to explain about the graph of the Chebyshev low pass filter. So this figure will show the magnitude response of the Chebyshev type 1, and with the same normalized passband edge, means that the omega p is equal to 1. When the filter order n increase, the number of passband filter will increase, and the roll-off rate will increase too.
Okay, my name is Majduddin, and I'm going to present about the transfer function calculations. Next. Okay, the low-pass Chebyshev filter is designed such that the following requirement is satisfied. F equal to 10 GHz, A max equal to 0.5 dB, Fs equal to 15 GHz, and A minimum equal to 20 dB, and the C gain equal to 5. So this is our givens. These values are given. We set it to design our Chebyshev filter. So first, in order to calculate the transfer function, we have to find the regular factor, which is epsilon. Epsilon is determined so that to control the amount of passband ripple. Next. How to get epsilon? Epsilon is actually determined using a specific formula, which is this formula. Epsilon equal to square root of 10 to the power of A max over 10 minus 1. A max from the requirement that we have is equal to 0.5. Then we substitute 0.5 in this equation. We find epsilon equal to 0.3493. Secondly, is to determine the order of the filter N. Next. To determine the order of the filter, we have to use this equation, which is A omega s equal to 10 log times 1 plus epsilon square cos square times n cos inverse times omega s over omega b. After we substitute epsilon equal to 0.3493 in this equation, we will find that n equal to 4.2. we assume that n equal to 4. But when we substitute back n in this equation, exactly here, we find that A omega s equal to 18.35 dB. This value is actually less than 20 dB. And thus we will not take this value. So we will again substitute n to higher number than 4. So we substitute n to 5, equal to 5. And when we substitute n equal to 5, we find that omega ws equal to 26.65, which is bigger, which is greater than 20 dB. And thus we take n equal to 5. The fifth order is selected instead of fourth, because we need to design a low pass filter that will attenuate at least 20 dB when it reaches the frequency of 15 kilohertz. The frequency of the stop band, if the fourth order is selected, when the filter only attenuates 18.3 dB when it reaches 15 kilohertz. Next. And finally, we have to determine the value for the volts. This equation is used to determine the value of the volts. Next. For B1 and B2, we use this equation. We simply just plug in some values. And also for BC next, we will do the same for BC, B4, and B5. And after we find all the value for volts, we have to substitute it in the transfer functions formula. Since the order of the filter is only fixed order, we need to determine a total of 5 volts for the transfer functions. Next. This is the formula for the transfer function. It's constant. This is the formula. Hs equal to k omega w to the power of n over epsilon times 2 to the power of n, which is the order of the filter, times s minus b1 times s minus b2 until s minus b5. And then we substitute our values here in this equation, where omega b go back, where omega b equal to 2 pi fb. That's all for my presentation. Thank you.
Okay, hi everyone. For today, I'm going to present about finding the components value and design of the Chebyshev filter. Okay, previously McDonald have already presented about the calculation, and now I'm going to show how the design could be. Next. Okay, as far as we concern, this is the first order low pass active filter and the second order low pass active filter. The difference between them is the first order you have one resistor. This is the configuration basically, and this is the second configuration, which refers to the second order. Basically, now we have three order and 5 stage of Chebyshev filter. These 3
C stage and 5.
Okay, just pause. Delete. Okay, hi everyone, I am Vikraman. I am going to present to you about the finding of the components value and the design of a Chebyshev filter. So previously my friend McDonald had already presented about the calculations on how to find the number of orders and all. So I am going to further into this schematic design. Okay, basically you have this Chebyshev filter have 5 orders and 3 stages. Why there are 3 stages? Because we have first order low pass active filter and second order low pass active filter. So in order to achieve 5 orders, you must have 2 second order and 1 first order. So altogether there will be 3 stages, but it will accumulate into 5 orders. 3 stages and 5 orders. Okay, let me explain what is first order and what is second order. The first order is the configuration is as such. This is the second order. We have we are only having 2 orders. One is first order and second order. Through that, we will try to come up with as much as orders that we require for that particular design of filters, basically. Okay, next. Okay, as what you can see here, this is T1 is term 1. So basically, this calculation is meant to be finding what is the value of R1 and C1. Basically, in our schematic diagram, we have the component R and C. R is resistant and C is for capacitor. So we have to instill some value. In order to find that value, we have to go through this kind of calculations in order to get the accurate or appropriate value. So as what we can see here, when we gone through, this is a non-formula. When we have compared the formula with the order that we obtained. This one we obtained from the first order calculation. When you compare them, we got to know that 1 over R1 C1, we will get this value because 0.3623 Vp is equal to 1 over R1 and C1. So we just comparing both formulas and we are getting into obtaining those values. So for now, we have to assume that we might not know there are two parameters that we should know, we should take into consideration. So what we are going to do now, we are just going to let the R1 is equal to be 1 kilo ohms. When 1 kilo ohms, we will tend to find what this C1 is basically. So from there we will be obtaining what is R1 and C1. Next. Okay, this is the second order. When the second order, we are going to do the same thing again. We are going to compare the second order formula with the second order, the one we obtained from the second order. So this is the value that we obtained from the second order. So we are going to compare again with the formula. This is a standard formula. So when we compare it, now the the formula is quite different. 1 over R1, R2, C1 and C2. So now we can see that there is two more parameters, R2 and C2. If you remember, this is the second order. Second order consists of two capacitors and two resistors. If you go back to my video, previous slide, you will find that first order consists of one resistance and one capacitor. Could you please go back? Okay, as what you can see, this is C1 and R1, whereas here you will find two resistance and two capacitance. Therefore, we name them as R1, R2 and C1, C2. This is the main difference. So this one was the first order and the other one now is the second order. Second order consists of two capacitors and two resistors. Okay, now we have to substitute again the value. Just now we have assumed R1 is 1 kilo ohms. And now we know that we got some values for C1. We are going to substitute R2 and C2 because it's now unknown value. So what we are going to do again is, we substitute this is k equal to 1. When k is equal to 1, because k is the number of order, now we are talking about the first order, we will get to know that we will get such a value without substituting R2 and C2. So the value is 0.5862 Vp, and now we want to let the R, we remain the R to be the constant all the time. No matter throughout the schematic diagram, we want R1, R2, or all the R's to be the same value. So again, we are calling back 1 kilo ohms of resistance, and we will obtain C1 and C2 respective values. So this is the R1, R2, we have the same value, C1 and C2 we have different values. Okay, now we have done for the second term. Now we are going for the third term. Okay, this is T3. Again, we are going to repeat the same thing, but we are going to get different values based on the previous calculation that we have made. So we are going to compare the two formula again. We are going to obtain R1, R2, C1, C2 again. That means R2 and C2, R1 and C2, and R2 and C1. So this is another configuration. Now the K is going to be 5. Why 5? Because we have 5 orders now. So when we do the calculation, it's 0.2239, where we obtain the value from here. Okay. Now the 5 came from here. This is the 5 because we are talking about the fifth order. So R1 and R2 is equal to 1 kilo ohms. So we will be obtaining C1, the value of C1 and C2. So this is the value 23 nanofarad and 10.6 nanofarad. So basically, we obtain all the values required for the schematic diagram. So after we have done this, now we are going to put the value into the simulation and see how the filter is going to take place. Okay. Next, this is the schematic diagram. Okay, as what you can see, we have put up a schematic. We have drawn the schematic diagram into this PSpice, and as what you can see here, these are the these are the second order. This is a second order filter. This is another second order filter, but this is a first order filter. Why I'm saying that? You know why? Because here I find two capacitors. Two resistors. The two capacitors here, the same configuration, and here we have only one capacitor and one resistance. So this is how you'll find whether it's first order or second order filter. Next. So when we do the simulation, we will get output waveform and unity gain. So now we are going to discuss about the output waveform and the unity gain. Okay. Now what you can see is there's a ripple on top there. So basically, this ripple is passband ripple. Whereby the passband ripple is up from here to this part is the passband ripple. So when the thing already start to be fluctuating to a very smooth graph, this is called the A max or the cutoff frequency FC. So this is the cutoff frequency. As it goes down, okay, this is going to be the passband. This one is going to be the passband. And this one is the this is going to be there is another frequency here, but there should be some ripple. But since there is no ripple, that means it's going to be a stable filter. There is no noise basically. So this is a very perfect graph that we obtained from. Okay, and this is going to be the stop band. I think the schematic is clear. The graph is clear about. The graph is, we find a very smooth graph, we obtain a very smooth graph. Then the next, we are going to talk about the unity gain. Okay, the unity gain, this is the pass band unity gain and this is the stop band unity gain. We found that the unity gain is 10 kilo and the amplitude is 0.5 and the stop band unity gain is 15.04. And the amplitude is minus 26.636. So this is what we get from out of the schematic diagram. So this is the unity. We have seen the output waveform as well as the unity gain. So that's all from now. That's all from me. Now I'd like to call upon Zuhairi to take over the presentation from here. Thank you.
Hi, I'm Muhammad Zuhairi. Will presenting about the conclusion part. So the first conclusion is the fifth order low pass Chebyshev filter is successfully designed using silent key configuration. The requirements set are satisfied by the performance of the filter design. The second conclusion is the low pass Chebyshev filter is successfully simulated by using PSpice and the waveform generated satisfy with the requirement. So that's all. Thanks for your listening.